I welcome you for the lecture series in the course Mechanics of Solids. Let us see the next topic in our Unit 3 torsion is shaft deformation. So we all know what is deformation. It is a change in shape due to the load. So understanding twist and stress in power transmission components, let us empathize this, what are the loading that is happening in a shaft. Here we have a circular shaft and twist due to torsion is shown in this arrow mark, which is equal and opposite side, and the deflection due to bending moment is shown in a line here. So this is due to transverse loads, that is because of gears, pulleys we have seen in the previous slide, and torsional loading is due to the twist happening in the torque, and axial loading is due to the attachment or the assembly with the shaft. So this is a common phenomena of loading in a circular shaft. So again, what is torsion? We'll just recap. And twisting action, apply torque twist shaft about its longitudinal axis, and the shear stress varies across the cross section unlike uniform axial loads. So these are all the real applications. One is power transmission, drive shafts, machinery. And let us go to slide number 3 and 4. We have already seen shear stress and shear strain distribution. So we have a center point, we have a shear strain that is equal to 0 at the shaft axis. Linear variation happens at the radial distance, maximum at surface, peak strain and stress at the outer radius. So this is the formula for shear stress. So coming to the polar moment of inertia, we have seen already, which is J equal to pi by 4 d power 4 divided by 32, and J equal to pi into d naught power 4 minus dA power 4 by 32, where d naught is the outer diameter and dA is the inner diameter. Larger the J means less twist and lower shear stress. So this is applied in all the design considerations. So what is angle of twist and the material properties? So the master formula is pi equal to TL by GI, and T is the applied torque, L is the shaft length, G is the shear modulus, and J is the polar moment of inertia. So longer shafts increase twist angle, stiffer materials higher G reduces twist, larger J decreases the twist. So this is all about this formula, and the engineering applications and design considerations. Power transmission P equal to torque into angular velocity. Strength requirements is shear stress maximum must not exceed yield strength. Surface quality, finish affects fatigue life and failure resistance. Weight optimization of the shaft reduces mass, maintains strength. So coming to the key takeaways of this particular lecture, we have a non-uniform distribution where shear stress and strain maximum at the surface, 0 at the center, that we have seen already. The geometry matters, diameter, hollow versus solid. These three different things, and material shear modulus governs the response. So the critical design parameter is angle of twist like torque, which links torque, length and stiffness. As we have seen, the formula for angle of twist is TL by GJ. And engineering excellence, understanding torsional deformation ensures safe, efficient shaft design. So this is the engineering excellence we have seen. And here is the mind map for this particular deformation of shafts, in which definition of this torsion is seen and deformation parameters we have seen, and geometric resistance, and the material and formula we have seen the master formula. Shear modulus represents stiffness. Shear stress is given by the formula T rho divided by J. And all these things are considered for the design, and based on the shaft types, we could look into the design. So the assessment part, the angle of twist theta of a circular shaft is subjected to torque is directly proportional to length, that is TL by Gj is the formula. And for a shaft length of L, modulus of rigidity G and polar moment of inertia J, the torsional deformation is given by TL by Gj, that is answer A. So I hope we have understood the deformation phenomena of a shaft. So these are all the references for this particular lecture. We'll meet you in the next lecture. Thank you.